So most of you have probably been using XY coordinates or XYZ coordinates for quite a few years. The idea of coordinates or Cartesian coordinates should be pretty familiar. Elsewhere in math, you probably learned other coordinate systems. I would assume most people have worked with polar coordinates. Those of you that have had Calc 4 would have also seen cylindrical coordinates and spherical coordinates. Those are other coordinate systems. In Calc 3, you learn a special coordinate system or concept where you learn about the TNB frame. That was the tangential, normal, and binormal components of a space curve. And they created a coordinate system for, that helps you understand a space curve or like an oscillating, the oscillating circle. Let's see. If you're in a video game, I'm not a game player, but I watch my son play all of his games, and he's always grabbing his ammo and grabbing his whatever bling or whatever all the stuff, and he's running through these little worlds, shooting all the bad guys somehow, which is quite rewarding, except for you get shot more often than you shoot somebody. But anyway, and if you can imagine this as you're running through your little 3D world in a video game, what's going on is you're always seeing the world through a different frame of reference or a different coordinate system, if you will. You've got your straight ahead component, the what you're seeing. You've got the right left based on where you are in the game. You've got the up down. And so the coordinate systems, there probably is some master coordinate system in the game, but presumably all those video games are also constantly drawing a picture for you on the screen based upon the reference system of your character, right? And so they're always thinking about these things. And so we're not going to be diving into the nuances of video games or those kinds of things. What we're going to be talking about is the general concept of coordinate systems, what all's involved with a coordinate system, and how we can go back and forth between various coordinate systems. And so this would be a concept that could get applied to various other applications. The other application I want to point out of coordinate systems is I think something you do in differential equations. I don't remember the name of it, but in differential equations, sometimes you'll end up in places where you'll be like, oh, this first term is going to be an e to the t, and the next one's going to be a t e to the t, and the next one's going to be a t squared e to the t, something like that. Does that sound familiar for those of you that are in DiffyQ? I'm seeing some nodding. And that concept again gets at this idea of a coordinate system, but now we're no longer in the coordinates in the usual sense. We're in coordinates where the coordinates are functions, not just vectors. So that's kind of some background stuff before we dive in. So I'd like to begin by working through this Theorem 7, which is the unique representation theorem. We've talked about it a little bit before, but what does the word unique mean in mathematics? Only one solution. Yeah, that's good, Megumi. So there's only one solution, only one possible way something can happen. So I think the word solution seems to imply that there's an equation involved. I think in this case, since we're going to be talking about a representation, we're going to say you can write it only one way. So you could represent it only one way. I think that's one reason a lot of people like math, is that, oh, there's only one answer. Oh, you can only write it one way. And sometimes people don't like math for the same reason. They're like, what? I want the freedom of English and language or whatever. But you're in linear algebra, so I would assume that more of you like the uniqueness of math. So we've talked about uniqueness proofs in the past. What's our general strategy for showing something is unique? Yeah, from Gerald, from Evan. So if we want to show something is unique, we basically will assume that it's not unique in some way, and then show that the two things we thought were not unique must be equal to each other in some sense. That's our general strategy. So here's the theorem. Theorem 7, the uniqueness representation theorem. So if we let B equal to B1 to Bn be a basis for a vector space V, then for each x in V, there exists a unique set of scalars C1 to Cn such that x is equal to C1 B1 plus ... Cn Bn. So here's our proof. Again, since it's a uniqueness proof, we're going to assume that things are not unique and show that that gives us sort of a contradiction. Here's our claim. Here's our proof. So I'm going to move up just for the sake of space. So let x in V be given. We're trying to show that it's unique. So what we're going to do is we're going to assume that there are two different representations. Okay, so we assume that there's two different representations for x, and specifically, these would be representations for x with respect to the basis B. WRT B. Have we used WRT before? Can't remember. Okay, so WRT is equal to with respect to. With respect to. So like back in calculus, we would take the derivative of f with respect to x. That's that WRT. So with respect to b. So what would this mean? Well, this means that there are a whole bunch of c's and b's. So we got x equal to c1 b1. Come on. Plus plus cn bn, and x is equal to d1 b1 dn bn. Come on. So what I'm saying is it's not unique because I've got one representation for x that uses yellow c's, and I've got another representation of x that uses blue d's. Well, that's all very interesting. Let's see if we can get 0 into the game. So one way of writing 0 would be x minus x. I don't think anybody's going to argue with that. And now I have two different versions. I've got the yellow version and the blue version of x. So this would be the same thing as c1 minus d1 b1 plus plus cn minus dn bn. Yeah, 1 plus 1. So a note from Andrew, he said the written assignment basically has him second guessing everything, including what 1 plus 1 is. I don't know if anybody's picked up the Logic Comics book that I mentioned, but Bertrand Russell and Alfred North Whitehead wrote a book called Principia Mathematica, and in it they spent the first, I think it was 362 pages. I could be off on my number, but I think it's 362 pages. At the end of 362 pages, they had proved that 1 + 1 = 2. That's how long it took them. 300. So we'll try not to go there, but if you're doubting yourself, you're not the first person. All right. So let's go back and remind ourselves what B is. So this B is a basis. What are the two characteristics of a basis? It's linearly independent. Good. That's the first one. And it spans the space. So it's linearly independent and it spans the space. So here we have an equals 0, right? So we have equals 0, which means we have a homogeneous equation, and we have vectors b1 to bn that are linearly independent. And so since we know that all those guys in B must be linearly independent, we must know that there are no non-trivial solutions, or there is only the trivial solution to the homogeneous equation. Okay. And so like Gerald is saying, this tells us that all of the C's are equal to each other. And so I might say that Ci is equal to Di equal to 0, or sorry, Ci minus Di equals 0 for Ci equals Di for I equal to 1 to n. Like all of those coefficients are equal. The yellow ones are equal to the blue ones. Okay. So what did we just do? We assumed that there were two representations, the yellow one and the blue one, but we just showed that the yellow one was equal to the blue one, which lets us conclude that the representation is unique. Yeah, it's a contradiction. We didn't actually assume that they were different, so we don't really need the contradiction symbol here, but we did assume that there were two of them, and we just showed that those two things are the same thing. But yeah, that's right, Gerald. That's right. Question? Very good. So we have this idea that representations of vectors are unique with respect to some basis. So now we need some notation to work with this. So definition. So suppose B equal to B1 to Bn is a basis for V, and X is in V. The coordinates of X relative to basis B, these are also called the B coordinates of X, are the weights C1 to Cn such that X equals C1 B1 plus plus Cn Bn. So we call this vector the coordinate vector. Okay. and that'd be the coordinate vector of x. And we want to make sure that it's clear what basis it's relative to. So we would say relative to basis b. And our notation for this will be like that. So we'll say x in the bracket with the subscript b is trying to tell you that you have you're giving you, sorry, let me start that sentence over again. X in the brackets with the subscript b says these are the coordinates of vector x in the coordinate system b. And these c's that are over here, these are, you can think about them, they're the weights or the coefficients on the various basis vectors. So this is also called the b coordinate vector. And so this mapping that we're talking about, where we have x going to xb, and here the key part is the little arrow, that's makes it a mapping, is called the coordinate mapping. Let me see if we can just do a simple aside example that might help you think about what this might look like. So if you have x equal to, let's think like xy, then just as in your old world, then think about like x in the polar world. So x in the polar world is going to have some like r theta. It's like we can kind of go back and forth. So you could start with your x, and you say, oh, I started with my x coordinates, and I'm going to go to my polar world. And I'm assuming people have done polar recently enough. There's no questions on this. This is a test question, just trying to make a connection. So polar. And you could ask, what's that transformation that lets you go from one to the other? Yeah, this is the same polar from pre-calc, exactly. Same polar from pre-calc. And so you're like, well, what's the mapping that we're talking about? Well, the mapping has something to do with how x is equal to r cosine theta and y is equal to r sine theta. Like, this is actually the mapping that goes from polar back to Cartesian. But this is like a world that's perhaps analogous, or a little bit analogous to an old world that you're familiar with that's analogous to what we're learning. Evan asked, this makes me wonder if Cartesian coordinates were always the standard coordinates. And I think what's actually important is to remember that coordinates are a relatively recent concept. That it's actually, I don't know if this story is true, but the legend is, at least, that René Descartes, the French philosopher and mathematician, that he liked to sleep in. He didn't like to get up early in the morning. I think he was a college student. And so his mom he's like, I do my best thinking when I'm laying in bed. And his mom let him lay in bed. And so one day he was laying in bed looking up at his ceiling, and there was a fly buzzing around in his room. And he's like, huh, I could talk about where that fly is on my ceiling just by talking about how far it is horizontally and how far it is vertically from some fixed point. That's why it's called Cartesian coordinates, because of Rene Descartes. So going back to Evan's question, were they always the standard coordinates? Well, they certainly weren't that before Rene slept in that day. And even afterwards, it would have taken a little bit to build things up. Good question. Let's keep going. So example 1. So consider a basis B, B1, B2 for R2. And here my B1 vector is 1, 0, and my B2 vector is 1, 2. And I want to suppose an X in R2 has the coordinates. So the B coordinates of X are -2, 3, and I want to find X. Let me look up so I can figure out my colors. So these are my weights, if you will. And so we would say that X is equal to -2 times B1, 0, plus 3 times B2. Okay, so I think I'm getting 1, 6. So again, the -2, 3 here, these are the coordinates with respect to B1 and B2. And the 1, 6, these are the coordinates with respect to the standard basis, E1, E2, or IJ, or XY, or whatever you want to call it. So notice going from the B coordinates back to the X coordinates was super easy, barely an inconvenience. How could I write this as a matrix product, since we're on a roll here? So it'd be like saying you had 1, 0, 1, 2 times -2, 3. Hey, something like that. And so this matrix right here would let us, this matrix lets you go from the XB world back to the X world. You started with your XB here, and we ended, our output was the X. Ahmed, I got a B times XB. Can you say a little bit more about that? Ahmed, I'm not tracking your comment there. I think so, yeah. What the matrix equation is. Yep. Yeah, so this would be transformation matrix times your XB, and that's going to give you out the X. Let's keep going. So So the entries of the vector x equal to 1, 6 are the coordinates of x relative to the standard basis E1 and E2. And the reason is because that 1, 6, if you will, would give me 1 times 1, 0 plus 6 times 0, 1, or 1 E1 plus 6 E2. And remember, when you see E1, we write E1 or E2, but you're thinking. Trying to think. You're thinking in this case, like, oh, this is the J vector. Or this E1 is the I vector, something like that. All right, and so we could graph these things with respect to their various grids. So if we wanted to graph the 1, 6 right here relative to the standard basis E1 and E2, like, oh, we're going to go over 1 in the x direction and up 6 in the y direction or in the E2 direction, and we have that point x. But on the previous page, we had, I don't remember what the color was, we had that xb was equal to -2, 3, I think. And so this is saying the -2 here is telling me I want to go -2 in the B1 direction. So if B1 is at this point, the -2 B1 would be here. And then I want to go 3 in the B2 direction. I want to go 3 there. So here's your B2. We want to go 3 in that direction. So that'd be 1, 2, 3. And so our point, same exact point, but it's now on the B graph paper. So, all right. So in example 3, we're given a B1 and a B2 and an X, and we're told that B1, B2 make up basis B, and I want to find the coordinates of XB, or of X with respect to basis B. This is the flip-flop of the previous question. So in the previous one, I was given the coordinates with respect to B, and I'm trying to find X. Now I'm given X, I'm supposed to find XB. So to do that, we can make it happen a couple different ways. So one solution is we can do this using row reduction. So if we want to do it using row reduction, you think about it and say, what is XB going to look like? So you're going to have some XB, and it's going to be some C1, C2, and that C1 is going to be the weight on the B1s, and the C2 is going to be the weight on the B2s. And if we add that stuff together, we should get out the 4, 5. Okay. But we could write this as a matrix. So this would be like saying, pardon me, 2, 1, 2, 1, negative 1, 1 times C1, C2 equals 4, 5. Well, we've solved these guys a zillion times. We can do this with row reduction, 2, 1, negative 1, 1, 4, 5, and it's an augmented matrix. Which will row reduce to 1, 0, 3, 0, 1, 2. What this is telling us is that the b coordinates of x are 3, 2. And those b coordinates are the same thing as the C1 and the C2 that were here. Come on. Graphically, the 3 is telling us how far to go in the B1 direction. And so here's B1. We're going to go three spots in the B1 direction. So 1, 2, 3. And then here's B2. So we're going to go 2 spots in the B2 direction. And so here's the point X. So this right here, come on, 2. This would be the graphical approach. Third way we could do this is we could do it using a change of basis matrix. It's funny, I didn't have the dead spot on my keyboard for a long time, and now it's back. Or on my touchscreen, it's back. Very weird. Shouldn't have restarted, I guess. All right, so there's something a little bit weird on this change of basis matrix. The matrix that I want, we're going to call P inverse B. And it's a little bit weird. You'll see why later down the road, but the one we're actually going to use is the inverse, not the actual PB. So let's see how this works. So remember what we did in the previous example. So if we took our change of basis matrix PB, which I'm about to describe, and I multiplied it by the B coordinates, then this would give me back my X. Okay. So you might say, Dusty, what the heck? Where did all that stuff come from? Let's go back in the notes for a moment to this example, example 1. So what we have here is we have our PB matrix, and we're multiplying by XB, and we're getting out X. Okay. And that PB matrix was made up by using the B1 and the B2. Let me see if I can highlight the new stuff. This is new, and this is new. Okay. Keep going, thumbs up. Okay, so where were we before? So in our case, what is this PB matrix? So it's going to be made up of the B1 and the B2s. So B1, 2, 1, B2, negative 1, 1. Okay. You see you're seeing that? So here and here. Okay. And then your XB is going to be what we're trying to find. This is what we're trying to find. And this is going to be equal to X, which we were given, and it's 4, 5. Okay. So if I want to find the green vector here, the green XB vector, then I think it should be clear that what I need to do is I need to multiply the purple vector by the inverse. So we have XB equals, come on, PB inverse times X. Okay. So we're saying that that XB is equal to PB inverse. So we need the inverse of this matrix. It's a 2 by 2, so we can just find our inverse. So determinant is 1/3. I've got a 1, or sorry, the determinant is 3, so I've got a 1/3 out front. And then I can swap the diagonal entries and change the signs on the others. Okay, so this is my PB inverse. And then my X is still the same friendly purple 4, 5. And so that if we do our multiplication, got 1 times 4 plus 1 times 5 is 9, divided by 3 is 3. And then negative 1 times 4 plus 2 times 5, 6, divided by 3 is 2. Something like that. Should it be negative? Should what be negative? Inverse. I don't think so. I think my inverse is okay. Yeah, I think my inverse is okay because I swapped the A's and the B's. And, yeah, so remember, so I guess this is an aside. If you have A, B, C, D, then its inverse will be the 1 over the determinants, 1 over AD minus BC. And then you have D and A, these two swap. And then you'll have negative B, negative C. These ones change sign. A coordinate system is a way of describing points, vectors, locations within a vector space. And so we have this idea of a basis. Do you remember, or I hope you remember, the two qualities of a basis? They have two main characteristics. Characteristic 1, they are linearly independent. And characteristic number 2, they span the space. And so once we have a basis in hand, we can talk about the coordinates of a point, of a vector, of whatever this thing is in the vector space, with respect to the given basis. And so when we were last together, we did this example where we said, if you have this basis B1 and B2 and some vector X, we could ask ourselves, how do we talk about vector X with respect to this new basis? And so we did it once using row reduction. We did it a second time. We answered the same question talking about it graphically. And we did it a third time using a change of basis matrix. And so what we were doing is we were saying, we're starting in this with some vector X, and we want to know, how do you write that vector X with respect to the new basis B? So it's B coordinate, so to speak. And we learned that the matrix PB gives us a way of, like a transformation that lets us go from the B coordinates back to the original coordinates. And good news, we can go the other direction from the original coordinates or standard coordinates to the B coordinates by using the PB inverse transformation. That's kind of where we left off last time. So the matrix PB changes the B coordinates of a vector X into the standard coordinates. Okay, so it's saying you're starting with the B coordinates and you're going to the X coordinates. And to do that, we follow that PB transformation. And we'll keep talking about that, so hang in there. So an analogous change of coordinates can be carried out in Rn for a basis B equal to B1 to Bn. So if we let PB equal this vector B1, B2, all the way to Bn, then the vector equation X is equal to C1 B1 plus C2 B2 plus plus Cn Bn. Make sure you're tracking. So these C1, C2, Cns, those are the weights of these basis vectors. And so we're saying that X in the B coordinate of X would be C1 to Cn. They're the weights that are associated with the B basis vectors. Okay. So this vector equation X equal to C1b1 plus C2b2 plus plus Cnbn is equivalent to PB and then the B coordinates of X. This notation right here is a little bit confusing to me. It looks like it's got a lot of characters, which makes it easy for you to forget what's going on. So remember that PB is a matrix. Okay. And that XB is a vector. So if I look at this and I think about how would I type this statement, I would need a P, and then I would need a subscript B, and then I would need a bracket, and then an X with an arrow over the top of it, and then an end bracket, and then a B with a subscript. So that's 1, 2, 3, 4, 5, 6 characters that I have to type in order to make this work, plus some formatting. But all it's saying is matrix times vector. It's sort of, in the old days, we would say something like, A times X, matrix times vector. It's that same amount of stuff happening. It's a special matrix, the PV matrix. It's a special vector, namely the B coordinates of vector X. Questions so far? So again, we call PB the change of coordinates matrix from B to the standard basis in Rn. So left multiplication by PB transforms the coordinate vector XB into X. Let me see if I can draw an analogy for you, because I think this is both easy but easy to be confused by. So think about your transformations. So we had T of X equal to AX. And so what this was saying is that if you started with some vector X and you multiplied by vector A, then on the back end, you would get T of X, which is the same thing as AX. So we were doing matrix multiplication in order to do a linear transformation. And specifically, the matrix that we're multiplying by, that A matrix, is on the left. It's on the left of the X. So when we come back here and it says left multiplication by PB transforms the coordinate vector XB into X, it's this same stuff we've been talking about. Since the columns of PB form a basis, they're linearly independent. And since they are linearly independent, they have an inverse, which leads us to the PB inverse times X equals the B coordinate of X. So this part right here is saying that we can come back with PB inverse. Questions? So let's talk about coordinate mappings. So choosing a basis V equal to B1 Bn for a vector space V introduces a coordinate system in V. The coordinate mapping x to xv connects this possibly unfamiliar space V to the familiar space Rn. And then you've got this figure here, and there's going to be more figures down the road. Let's look, I'd like to come back here, but let's look at example 4 for a moment, because I feel like this helps a little bit. So if you look at example 4, it says let B be the standard basis for the space P3 of polynomials. That is, B equals 1, t squared, t cubed. So we're starting in this world of P3. Okay, and things that live in P3 are of the form A naught plus A1t plus A2t squared plus A3t cubed. Okay. And so I could ask this question, are these blue guys vectors? So are these vectors? In a traditional sense, are they vectors? Not a trick question. Yeah, no, I mean, we could call them vectors if we want, but they're not really vectors in the traditional sense. They don't have, they're not tall and skinny with brackets around them. They don't have angle brackets on them. There's no ij's and k's. It's a polynomial. So it's a function. Okay. So they live in this world of P3, but we can go back and forth. And so we can go back and forth with another space over here, or we could say that this blue A naught plus A1t plus A2t squared plus A3t cubed is in some way analogous to this P with respect to the B coordinates, A naught, A1, A2, A3. So this one's, it's not a vector, and by vector I just mean kind of like in the traditional sense. Whereas certainly this one down below is a traditional vector. Okay. That makes sense? Let me make sure you're tracking what that would mean. So for example, what would 1, 0, 2, 3 translate to in this context? That would be like 1 plus 0 t's plus 2t squared plus 3t cubed. Yeah, thank you, Gerald. Yeah. So notice that what we're doing is we're saying that you can go back and forth between P3, the world of polynomials with degree 3, and which other space? What other space can we go back and forth between? Yeah, from Felix and Evan, we can go back and forth between P3 and R4. Okay. This bit where you can go back and forth between the two systems is what we call an isomorphism. It's a long word. Okay, so it's saying at some level, everything we can do in the polynomial world, we could also do in the vector world. Everything we could do in the vector world, we could also do in the polynomial world. We can go fluidly back and forth as long as you know how to translate. Here's a bad joke. So what do you call someone that speaks 3 languages? What do you call someone that speaks 3 languages? Trilingual. Thank you. Seche, Gumi, Matthew. What do you call somebody that speaks 2 languages? I'm getting it from Abe and Richard and others. What do you call someone that speaks 1 language? From Megumi. Yeah, American. Yeah. So this is a place where I'm an American. I only speak 1 language. I'm not proud of the fact. It's just true. But if at some level you can think about, for most Highline students are at least bilingual, right? And for those of you that are at least bilingual, not Americans like me, then at some level you are able to translate between your concept. You're hearing something in English, and then maybe it's going to Vietnamese, and then it's going back to English when you talk, or Spanish, or whatever your languages are, Ukrainian, whatever. And so there's almost like an isomorphism between the 2 places, right? And so where does that translation happen? Well, you might hear something in your ears and say something out your mouth, like those are the things you're writing or doing, but the isomorphism is almost like it's happening in your head, right? That we can't see that transformation happening between the 2. We could make it explicit using Google Translate or something like that, but that's what's going on. So let me go back to where we left off. Okay, so choosing a basis V for a vector space introduces a coordinate system in V. This would be like saying on the left, you might have the world of P3, and on the right, you might have the example of R4. And so we can have this new name for a polynomial or whatever, but now it's going to be with respect to more traditional vector. If we let B equal B1 to Bn, and it's a basis for the vector space, then the coordinate mapping x going to xb is a 1-to-1 linear transformation from V onto Rn. So again, in our example, your V was the P3, and onto Rn, that's the R4 in our example. And the key word in the middle here is you have this 1-to-1 and onto. And so we say that a 1-to-1 linear transformation from V onto W is called, here's our word, an isomorphism. It's like a translation from one language to another language, if you will. And it's important because you could go back again. So, if I'm talking to, I don't know, Ahmed, what's your first language? Just guess. Maybe it's English for all I know. I don't know. But what's your first language? Somali. So your first language is Somali. So, I say something, maybe when you first grew up learning Somali, I say something in English in your brain, you translate it into Somali, you do something over there in your Somali, you know, in your home or there, and then you come back and you have to translate it back to English. We can go back and forth. Or maybe the conversation starts the other way. You got a question, at least it's in your brain in Somali, you translate it in English for me, the American, and I'm saying American because I'm one language, not because I'm, not as a litmus test. It's a dig on myself in case that's not clear. Translate for me, I do something, say it back again, and then you put it in your native language. So what I've been told, I haven't really experienced it, but what I've been told is that when you're learning a new language, you truly get it when you start to dream in the new language, right? So your first language is Somali. When you start to dream in English, then I guess that means you understand English, like you're totally there. If your first language is Vietnamese, you start to dream in English. I guess I'm sorry, because I know my dreams aren't that great, so I hope you're not having my English dreams, whatever. Anyway, the idea is that translation is going back and forth. That's like the isomorphism, and it goes both directions. We can go from English to Vietnamese and back. We can go from English to Somali and back and forth. One's not better than the other. They're isomorphic to each other, at least by analogy. Yeah. Two spaces are indistinguishable. Let's keep going. So let's see if we can use it. Let's look at example 5. So if I want to use coordinate vectors to test the linear independence of a set of polynomials, we could start with these polynomials, and we could take advantage of this isomorphism, and we could write this first vector as what? What would be its b vector? I got 1, 0, 0, 2. And then the next one is isomorphic to 2, 1, -3, 0. And the third one, thanks, I'm looking at the chat, know your comments, but I appreciate all the input. What's the first component in the third vector? First component is a 0. Remember the place, remember you got to get your order right here. So 0, -1, 2, -3. Don't miss that 0 that's there. And so we could take these 3 vectors, -1, not -3. Thank you. Got it. Yep. Thanks, Ryan. Okay. So we could take these 3. Reading Hui's question. So Hui asked, is it because we know it's going to be R4 that we know the fourth one on P2 is 0? It's a good question. When I look at this, I would see the T cubed. I'd see that would be the highest power. And so I got to make sure I at least go into R4 in order to be able to fit third degree polynomials. I guess I could choose to go into R5 and have a whole bunch of zeros in that next component if I wanted to. Did that answer your question, Hui? Very good. All right, so if we want to know if these are linearly independent, okay, we could try to solve some system. We could say, remember, you could solve AX equals 0 and ask, are there non-trivial solutions? Okay, so we have 1, 0, 0, 2. And you have 0. Okay. This lets us row reduce. And so we can row reduce text in style. When you row reduce text in style, you can get 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. What does that mean? So it means the
Dusty, how come we had 4 rows and we went from 4 rows to 3?
Because I don't know, because I made a mistake. Thanks. I think that was Abed. Thank you. So from Gerlin, that there means there's no free variables. From Hui, it means that we have only the trivial solution to the homogeneous equation. Both are correct. And so what this tells us is, it tells us that these vectors, the vectors are linearly independent. And since the vectors are linearly independent, that tells us that the polynomials are also linearly independent. What does it mean? What does it mean for polynomials to be linearly independent? One x-intercept. Not so much one x-intercept. Like, what would it mean if vectors were linearly independent? Does something have only the trivial solution? So they're not the same. We'll talk about a basis in a second. So maybe Evan, I think, is dead on. You cannot make one from the others. So you have a blue polynomial, a purple one, and an orange one. And what the fact that they're linearly independent says, you cannot make the orange polynomial by just combining the blue and the purple one. You can't make the purple one just by combining the blue and the orange one. You can't make any of those polynomials from the other ones. Does that make sense to everyone? Okay. Let's keep going. So we learned that they're linearly independent. The next question is this a basis for P3? Is this a basis for P3? Why not? Gotta know why not. I've got that they don't span R4 from Megumi. So remember those three vectors. So So these guys right here were isomorphic with 3 linearly independent vectors in R4. Okay. So since there were, yes, they were linearly independent, but since there were only 3 of them, that tells you that they did not span R4. So since they don't span R4, certainly they're not going to be a basis for R4. So, it's not a basis for R4. And we've learned that P3 is isomorphic with R4. The spaces are interchangeable. So since they're interchangeable, what does that tell us about this being a basis for P3? So yes, the same thing applies. No. 3 polys can't span P3. So the key is that it does not span. Questions? Okay. Okay. So let's look at another example. Example 4. Let's let V1 equal to 362, V2 equal to -101, and X equal to 312.7. And then we'll let B equal the set V1 to V2. So one thing I want to point out is that the V1 here and the V2 are not scalar multiples of each other, right? I don't 3 times, they're not on the same line, if you will. So we can just observe that V1 and V2 are linearly independent. We can just see that. When there's 2 things, you can just see whether they're linearly independent or not. If there's 3, you're going to have to work a little bit harder. So we know V1 and V2 are linearly independent. And so we would say that B is a basis for H, where H is the span of V1 and V2. Okay, so I want to determine if X is in H, and if it is, find the B coordinate of X. Okay, so let's start by doing this by row reducing. Remember, there were 3 different methods. So we could do this by row reducing. So if we do it by row reducing, we think that how do you do it? Like trying to figure out how to say it. So we have P B times X B equals X. And so our PB is going to be the 362 and the -101. And we're going to augment with our X 3, 12, 7. And when we that's what we're trying to figure out. Croy said X should also be linearly independent. That's what we're trying to figure out. It may be, it may not be. Okay. So when we do this, we can row reduce, and we end up with 1, 0, 0, 1, 0, 0, 2, 3, 0. Okay. So what does this last row being all zeros tell us? It says that we're consistent. And so the first part was, let me determine if X is in H. So it's determine if X is in H, it's consistent, so that's telling us that X is in H. Okay. That part's so good. Then the next part says, to find the coordinate vector of X relative to B. So find the coordinate relative to B. So what we're saying is that XB is equal to 2, 3. And specifically what that's telling us is it's telling us that X is equal to 2 times 362 plus 3 times -101. Okay. So this lets us find the coordinate vector of X relative to B. All that is following kind of a row reducing method. Croy was asking about determinants and whether the last column should be 0. Hold on to that thought for a second because there's something interesting going on here. So let's make sure you're seeing what's going on. So we're saying X is equal to 2 times 362 and 3 times -101. So it's saying we want to go like this would be 2 in the V1 direction. So here's the V1 direction, and we want to go to that direction. And then we want to go 3 in the V2 direction. So 1, 2, 3. So here's that point X. And this point X it has coordinates 3, 12, 7. It has B coordinates equal to 2, 3. Nice. All right. Last thing that I want to say here is that we've solved this question, 1, using row reducing. 2, we've done this with graphing. But notice that 3, using the PB inverse, fails. Why does it fail? Yeah, notice that your PB matrix, that PB is this yellow matrix. It's not square. So there is no inverse matrix in this case. And the reason it's inverse is because your H space that we're talking about is only a 2-dimensional subspace. It doesn't actually fill out all of R3.